Thank you very much. Thank you very much to the organizers for organizing such a wonderful conference and for giving me the opportunity to speak here. I'm going to talk about holographic orbifold CFTs, and this talk is going to be based on a series of papers written with Beatrix Mühlmann, Thomas Gemünden, my student, Alex Bella, Alex Maloney, and Aida Saleh. So the basic goal of this work, of this series of papers, is to try to find new examples of conformal field theories in 2 dimensions, which could potentially serve as holographic tools to some theory of gravity in ADS theory. In particularly, we are interested, and this is sort of the guiding principle of this talk, we're interested in theories which have very few light states. And as you will see, it's actually quite difficult to construct such theories. The way we're going to construct such theories is by using orbifolds. And basically, the main part of this talk is going to be, I'll describe various constructions of orbifold theories and what their light spectrum looks like. And finally, if there is time, I will also talk about a little bit about the application of such theories, basically computing partition functions and looking for phase transitions. Let's get started on the first part. Let's get started on orbifolds and their spectrum. Just to get it out of the way, even though we won't mention it too much explicitly, sort of at the back of everything what we're doing is modular invariance. So modular invariance is going to be the central tool of all our constructions. And as you probably all know, if you write down the partition function of a 2D CFT, and using this convention here, where tau is a complex parameter in the upper half plane, where physically you can think of the imaginary part to be roughly the inverse temperature beta, and the real part roughly as spin potential. Then, when we define a partition function this way here, it turns out that this partition function has a very nice property, namely it's invariant on the modular transformations. So z of a tau plus b over z tau plus d is equal to z of tau, as long as a, b, c, d's are the entries of a SL2Z matrix, that is as long as a, b, c, d is an element of the modular group. So as Jeff already pointed out this morning, there's basically 2 generators of the modular group, the S transform and the T transform. We won't worry about the T transform too much, it won't tell us too much, but we are very much interested in the S transformation. The S transformation is simply taking tau and send it to -1 over tau. So physically you can think of it as some sort of high temperature, low temperature duality. Now this is sort of a statement on the free energy, some invariant statement on the free energy. What we're interested in is the spectrum, so we want to translate this statement into some microcanonical statement, so a statement about the spectrum, the growth of the number of states. And in particular, what this invariance here implies is that the spectrum has Cardi growth, so-called Cardi growth, for very heavy states. So Cardi growth is essentially e to the square root of h, so the number of states grows like e to the square root of h. And this is valid, this is universally valid if the states are very heavy, that is h and h bar are much bigger than the central charge. And for holography, this is actually crucially important because this behavior is exactly what's needed in order to explain the entropy of black holes. However, even though this explains the entropy of black holes in this regime, this is not necessarily the regime that we're really interested in holography. I mean, we may be interested in that regime, but there are also other regimes that are of importance in holography. In particular, in holography, usually what we want to do is we want to consider some classical or semi-classical limit, which in this case means we want to send the central charge to infinity. And then h, the weight of the states, or the mass of the black holes, or of the states if you want, they don't have to be necessarily much bigger than c, so they don't need to be parametrically bigger than the central charge. For instance, we might be interested in lighter black hole states, where, say, for instance, h is of the same order as the central charge, or we might be interested in perturbative states, say h is much smaller than the central charge. For instance, we could take h to be fixed, and then send c to infinity, and then we could try to wonder what happens, for instance, to the number of such light perturbative states. So just to be more precise about the terminology, I'm going to call light all the states for which the weight is smaller or equal to c over 22. And we'll see in just a minute why this definition is very useful and makes sense and allows us to use powerful mathematical tools. So the point is that this Cardi formula is valid, universally valid for very heavy states. So basically what this tells us is that modular invariance essentially fixes the heavy part of the spectrum, the heavy states. But it does not really fix the light spectrum. So potentially, even though the partition function has to be modular invariant, we have a lot of choice for the light states of the spectrum. There is some sort of slogan which is, in some cases, is actually correct. In other cases, it's only morally correct. And the slogan is something like the light spectrum fixes the heavy spectrum. So one case where this slogan is actually precise, and this is actually also the case that I will mostly talk about, are so-called holomorphic or chiral conformal field theories. So these are conformal field theories where essentially the left movers and the right movers factorize, so the holomorphic and the anti-holomorphic part factorize. And in particular, the partition function itself, well, either you can consider it to be something holomorphic times something anti-holomorphic, or you can just forget about the anti-holomorphic part and just consider the holomorphic part. And in that case, the partition function is, well, it's almost a holomorphic function. It does have a pole at q equals 0, which comes from this q to the minus co with 24 prefactor. So this is what's mathematically often called a weakly holomorphic function. And the point is that these weakly holomorphic functions are completely fixed by the polar part at q equals 0. So concretely, if we write down this holomorphic partition function here, we find that if we fix the coefficients AH, where A for the coefficients for H equals 0, 1, 2, and so on, all the way up to C over 24. So if we fix exactly the coefficients that correspond to what we define to be the light spectrum, then the partition function is completely fixed. There's a unique modular invariant function which has that polar part. So in that sense, this slogan that I presented on the previous slide is exact. The heavy spectrum is completely fixed by the light spectrum. And there is actually a converse statement. So this is a statement about uniqueness of such a partition function. There's also a statement about existence. Basically, we can pick whatever light spectrum we want. We can fix those coefficients any way we want. And we will always be able to write down a modular invariant function which has that polar part. And in fact, this construction is very explicit. One way to do it is you can take the so-called Hauptmodul, the Klein J invariant, and then just express the partition function, the weakly holomorphic partition function, as a polynomial in this Hauptmodul here. As I already mentioned, so these holomorphic or chiral CFTs are essentially everything I'm going to say I will express in the language of holomorphic or chiral theories. Some of the statements actually also hold for non-holomorphic theories, but for convenience, I will just restrict in what I'm presenting here to such holomorphic theories. The point is that for non-holomorphic theories, sort of the slogan is no longer exact, but there's still remnants of the slogan available. The point is, in the holomorphic case, it really worked because the space, the vector space of weakly holomorphic modular functions of a fixed pole was finite dimensional. But this is no longer the case in the non-holomorphic case. So the situation is much more complicated. There are still remnants of this idea that the light spectrum fixes the heavy spectrum. That's actually behind the modular bootstrap. But usually you have to impose some additional constraint, like for instance, you have to assume that the spectrum is positive. Okay, so the message here was that even though modular invariance fixed the heavy states, it did not fix the light states. So a priori, in particular, say for a holomorphic partition function, there's almost no constraints on how we choose the light spectrum. So in particular, if we want to start from a certain bulk theory, which has a certain growth, we can always try to model at least the light spectrum of that bulk theory on the CFT side by simply imposing that particular growth. And by this existence theorem, we have a guarantee that we will always be able to write down a modular invariant function which has that light spectrum. So for instance, what we could do is if we think that our bulk theory is very stringy, then we would expect some sort of Hagedorn growth of the light spectrum. So the log of the number of states, or the entropy if you want, will be linear in H. We could also ask for something which maybe grows faster than Hagedorn growth, some sort of super Hagedorn growth. Or we could ask for slower growth. And in fact, that's what we'll be mostly interested in. Here, we're interested in few light states, so we're mainly interested in trying to look at theories which have slower growth. For instance, what you could do is you could try to mimic the growth that you would expect from a local quantum field theory in d dimensions. So you'd have something like entropy with like h to the d minus 1 over d, which is slower than Hagedorn growth, of course. Or if we're very ambitious, we could also try to find extremal CFTs, as Jeff already mentioned this morning. And in this case, basically what we want to do is we only want to have gravitons, boundary gravitons, and it turns out that the growth of state is 2 pi times h over 6. Now the point is just from modular invariance, we can always write down, as I pointed out, a modular invariant function, which does have this light growth. But the central question is, well, simply because we can write down, only because we can write down such a modular invariant function doesn't mean that there is a corresponding conformal field theory which has this partition function. So the central point of this talk really is the question, can we actually construct CFTs that have such partition functions? And so let's just look at various examples. Let's start out with the example which is probably most familiar, the most familiar example, namely the symmetric orbifold. So what's the idea here? Let's start out with our favorite conformal field theory, which I'll call V. Often I will also call this conformal field theory the so-called seed theory. Then what we can do is, in order to have some family where we can define some large n or large c limit, we can just simply take the tensor product of n such theories. But this tensor product is definitely not a good holographic tool. It doesn't even have a well-defined large n limit because the number of light states diverges as we send n to infinity. So somehow we need to get rid of a lot of light states so that we have at the very least a finite number of light states as n goes to infinity. So one thing we can do is we can orbifold. And orbifolding is, roughly speaking, something like gauging a discrete symmetry or finite symmetry of the theory. So one symmetry of this theory is, of course, it's symmetric on the permutations of the factors. So Sn, the symmetric group of n elements, is going to be a symmetry. So what we can do is we can orbifold. Orbifolding, I'll come back to that in more detail. In the first step simply means we throw out all the states which are not invariant under the symmetry group. And indeed, one finds a well-defined expression for the partition function, originally due to Dijkgraaf, Moore, Verlinde, Verlinde. There's actually also, that will become important in just a minute, a version for more general permutation groups. So this, and in particular, this has a well-defined large n limit in the sense that you will only keep a finite number of states. So now the question is, what does the light spectrum of the symmetric orbifold look like? It actually, at least to leading order in n, it has a very nice and simple formula. Turns out that the light spectrum actually has Hagedorn growth. More precisely, the light states grow like e to the 2 pi times h. The heavy states then, as expected, grow like you'd expect from the Cardi formula. So this shouldn't come as a surprise, but what is a bit surprising is that usually for a generic conformal field theory, you'd only expect this Cardi growth to be valid for very heavy states, so when h is parametrically larger than c times n. For symmetric orbifolds, actually it already kicks in at Cn over 12, so in a sense the Cardi regime is maximally extended. I'll show a graph of this in just a second, but the other important point is actually that this seed theory that we picked, this V, whose tensor product we took, actually doesn't really affect, at least the leading order in n, doesn't affect the outcome. So no matter which theory you pick here, for instance, probably the natural choice that you would have made is, for instance, a nonlinear sigma mod 1 K3 in order to describe the D1, D5 system. You do get this answer, but also if you pick a completely different conformal field theory as your starting point, you still get the same answer. So just on a plot, basically what you see here, the light states have this Hagedorn growth, this linear growth, and then the black hole growth kicks in almost immediately. Let me maybe make a small side remark. So very importantly, what we're discussing here is the full partition function. So we're really counting all the states, supersymmetric or not, of the theory. If you repeat this procedure, but rather than computing the partition function of the symmetric orbifold, you compute the elliptic genus, then the outcome is actually quite different. Turns out if you do this procedure for K3, the symmetric orbifold of K3, and you compute the elliptic genus, then you find that the light spectrum does not grow exponentially like Hagedorn, but it actually grows like, the entropy grows like square root of h. And this is actually important because this allows the precise matching of the number of states to the supergravity states. So the point is that there are so many cancellations in the elliptic genus that most of this exponential number of states simply cancel out. The other interesting point here is that I stressed that previously for the partition function, the result was essentially independent of the seed theory that we chose, but it turns out for the elliptic genus it makes a big difference. So this is true if you start out with K3. If we start out with a higher dimension calabi-R, when take its symmetric orbifold, then generically we will get a different behavior. Namely, again, we'll get Hagedorn growth. Okay, but let's return to partition functions now. So we found at least one of our desired growth. We did find a model, a corresponding model, namely for the Hagedorn growth. But now we would also like to find the different growth behaviors. And as I pointed out, there's a certain way which we won't be able to find such a different growth behavior, namely, we cannot simply exchange the underlying seed theory because the growth is always the same. What we can do, however, we can try to orbifold by a different group. In particular, we had this full symmetric group Sn by which you orbifolded, but what we could try to do is simply orbifold by a subgroup of the symmetric group, that is a permutation group. If we do that, the first thing to note is that actually we can choose Gn or the family Gn's arbitrarily. In a sense, we have to choose them large enough, because if they're too small, then what will happen is that we will not eliminate enough light states such that there is a well-defined large n limit. And a family of permutation groups which has the property that you're left with a finite number of light states is called oligomorphic. So for instance, Sn, the full symmetric group, is oligomorphic. If you go back and look at the original expression, you'll find indeed that you have a finite number of states, even as you send n to infinity. However, if you pick a very small subgroup of Sn, say for instance just a cyclic group Zn, then what you find is that this no longer works, because already at level 2 you will have a diverging number of light states. So there is a certain constraint. We need to find a family of permutation groups which is large enough so that we have a well-defined large n limit. Now the question is, can we do that? And presumably there should be a vast number of such oligomorphic families of permutation groups out there. Finding them and finding explicit expression is not that easy, but there's at least two types of things you can do. One thing is you can take the so-called direct product action of the symmetric group. So how does that work? We have our n factors, and let's take n to be a square number for simplicity. Now what we want to do is we want to arrange those n factors in a matrix, which is a square root n times square root n matrix. And now what we can do is we can act with two copies of the symmetric group of square root n elements. One of them acts on the columns, and the other one acts on the rows of this matrix. And this defines the so-called direct action on the factors. And it turns out that this is actually oligomorphic. And fairly obviously, we cannot immediately generalize this if we don't take a matrix, but some higher rank tensor where each copy, so there's going to be d copies of this, and they're going to act on the various indices of the tensor. And what you find is you do indeed get a different growth. So the problem with these theories is usually the untwisted sector is under relatively good control, but the twisted sector, computing the multiplicities in the twisted sector is somewhat difficult. So what we did here is we just computed the multiplicities in the untwisted sector, and this gives a lower bound on the number of states. And already this lower bound we see has faster than Hagedorn growth. So it grows like h times log h rather than just linearly h. So there's also a different thing, the so-called wreath product action, which grows a bit more slowly, which again turns out to be oligomorphic. So let me just quickly show you a plot. So this is for n equals 16. And here I'm plotting the actual spectrum of both the twisted and the untwisted sector. And there's maybe two things that, it's a bit out of focus, but that you could see. The first thing is maybe that it seems like there's not too much difference between the different types of things that we're doing. So we have the full symmetric group here, we have some wreath products, we have some direct products. So there may not be too much difference, but this is a logarithmic scale, so there's actually quite a big difference between the number of states between these things. The second, and in a sense more important observation is, and maybe you won't be able to see, but the theory which has the fewest number of light states here, at the very bottom here, is actually the full symmetric orbifold. And apparently if we do anything else, at least for these different families here, we seem to get more states, more light states, which is of course goes in the wrong direction. We would actually be mostly interested in theories which have fewer states than the symmetric orbifold. So you might suspect that permutation orbifolds won't gain you much when trying to construct theories with few light states. And in a sense, that's true. One can actually show that there is a theorem, one can prove a theorem which tells you that if you take a oligomorphic permutation orbifold, that is a permutation orbifold with a well-defined large n limit, the number of states grows at least as fast as h, so the logarithm of the number of states grows at least as fast as h over log h. So in principle, this theorem leaves you a little bit of wiggle room. You could grow slightly slower than linearly in h, but not by much, because h over log h is not that different from h. So basically, this result tells us that if we want to have a drastically slower growth of the number of light states, we need to construct and investigate more general orbifolds. So far, the advantage of permutation orbifolds was that we really didn't need to care too much about which seed theory we picked, because the symmetry came just from the permutation symmetry of the factors. But now if you want to go beyond permutation orbifolds, we have to be more specific. We have to look at more specific families of conformal field theories whose orbifold we can consider. And the type of families that we want to consider are lattice conformal field theories. So what do we want to do is we want to restrict again to holomorphic conformal field theories. And then there is a statement that if you have a lattice of rank d, of dimension d, which is even and self-dual, that is, its dual lattice is equal to the lattice itself, then from this lattice, from this even self-dual lattice, it could also be positive definite, I haven't spelled it out explicitly, from this lattice we can construct a holomorphic conformal field theory. And essentially, from a physicist's point of view, this is simply taking the free bosons and compactifying them on the space Rd modulo the lattice lambda. And it turns out if it's even and self-dual, then the resulting theory is indeed holomorphic. Now, remember, what we're still aiming to do is we're aiming to find theories which have very few light states. And basically, the point is that the vectors in the lattice correspond to states in the vertex operator algebra, in the conformal field theory. So if you want to have few light states, that means we need to consider a lattice which has only few short vectors, or optimally no short vectors at all. Now the point is, there is an inherent tension between trying to have a lattice which doesn't have any short vectors and the requirement that it is self-dual, because if all the vectors are long, then potentially the dual lattice will have a lot of short vectors, and then of course the lattice is not self-dual anymore. And there's a way of making this tension very precise using the fact that the so-called lattice theta function, which is essentially the generating function of the number of lattice vectors of a certain length, is a modular form of a certain weight. And it turns out that the best one can do is one can look at so-called extremal lattices. And extremal lattices are lattices which have, of course, a zero vector in them. That's always there. But then they don't have any vectors of length 2, length square 2, length square 4, etc., all the way up to vectors of length square 1/2 d over 24 plus 1. So in a sense, this is the lattice analog of the definition of an extremal CFT that Jeff showed us this morning. But now, basically, it's the same problem as we had before, simply because we can write down some modular form which looks a bit like a lattice function. Here, a lattice data function, there's no guarantee that a corresponding extremal lattice actually exists. So what is the status of extremal lattices? Well, in D equals 24, there is the famous Leech lattice, which is the unique extremal lattice in D equals 24. For D equals 48 and 72, 5 explicit examples have been constructed, maybe by Gabriele Neve. And one can actually show that unlike with extremal CFTs, this construction of the lattice data function goes wrong if D is large enough. So basically what happens is we get negative coefficients in front of some of the terms, which means we can't interpret it as a lattice data function anymore. So if D is large enough, there's a proof that such extremal lattices do not exist anymore. D large really means quite large, something of the order of 20,000. Okay, so, but that doesn't bother us too much, because what we're going to do now is we're going to concentrate on those 5 known examples of extremal lattices, and we're going to construct their corresponding vertex operator algebras, lattice vertex operator algebras, lattice CFTs, and we're going to construct as many of their orbifolds as we can. However, just just constructing the lattice CFTs is not good enough. So even though we do not have any light states coming from the lattice vectors, we still have a lot of light states simply coming from the free boson descendants, from the Heisenberg algebra, if you want. So to be more explicit, the partition function of the lattice conformal field theory is the lattice data function in the numerator, and that's good because, as you saw, the first couple of terms there vanish. But then we have, from the free boson descendants in the denominator, we have the dth power of the eta function, which in general will introduce a lot of light states. And in order to get rid of as many of those light states coming from the free bosons, we need to orbifold by symmetries of the lattice. Now, before when I discussed permutation orbifolds, I was very vague and didn't try to give a mathematical precise formulation of what's going on. And here we want to be a bit more careful because what we're doing here are chiral orbifolds, that is, or asymmetric orbifolds. That is, we're treating the left movers and the right movers quite differently. And as you probably know, such orbifolds are more subtle, so one has to be a bit more careful. Things can go wrong, anomalies can occur, etc., etc. So let me give you a very brief mathematical overview of the theory of orbifolds. And basically, mathematically, a two-dimensional conformal field theory is described by two structures. First of all, there's a vertex operator algebra, which physically corresponds to the symmetry algebra, or W algebra, or chiral algebra of the conformal field theory. And then secondly, what we're interested in is modules, so in a sense, representations of this vertex operator algebra. And physically, those correspond to primary fields. And then to get a conformal field theory, you combine both the primary fields, that is the module, and the original vertex operator algebra in an appropriate way. And actually, we want to restrict here to holomorphic CFTs, and we also want to make some more technical assumptions. I'm going to dump the technical assumption simply in the adjective tame. So roughly speaking, a vertex operator algebra which is tame is physically well behaved, which means that the modules form a modular tensor category, so there's a Berlinde formula, etc., etc. And in particular, as I said, we want to restrict to holomorphic CFTs, and for holomorphic CFTs, basically V itself is the only irreducible module. That is, V describes the entire conformal field theory, which is why sometimes I've been using VOA and CFT interchangeably. Now we want to find some orbifold. So for that, we first need to construct a symmetry of the vertex operator algebra. And we're starting with lattice theory, so a very natural way of constructing symmetries is simply we take a symmetry of the lattice, and then we try to lift it to a symmetry of the corresponding vertex operator algebra. And this lifting is, in general, slightly non-trivial and actually leads to an interesting and quite useful subtlety. So if sigma is an automorphism of the lattice, and roughly speaking, E sub V is the vertex operator corresponding to the lattice vector V, the lifted automorphism, say sigma hat, we want it to act on this vertex operator, of course, in the way that it maps V to sigma V. But in general, we can also allow for a phase factor in front of it. And this phase factor, in some cases, it's optional, but in other cases, it's actually crucially needed. The point is that this phase factor must be compatible with the cocycle of the lattice vertex operator. So if you define a lattice vertex operator, you have to make sure that what you define is actually local, which means you have to introduce some cocycles, some two cocycle, in order to ensure locality. So in a lot of cases, or at least in some cases, U of V can be chosen trivially, but in some cases, you cannot do that. In particular, if this condition here is not satisfied, we need to pick non-trivial phases U of V. And then in that case, for instance, what often happens is, for instance, that the group generated by the lifted automorphism is an extension of the original unlifted group. That is, for instance, the order of the generator is twice the order of the original. So in some cases, we're actually forced to do that. But more generally, we can also try to find more general phases. So lifting, we could try to find more complicated liftings of the automorphism. Of the underlying lattice. And that actually will turn out to be quite useful in just a second. So the next step is we actually want to orbifold by this symmetry. We say let's take G to be the group, some automorphism group of the actual vertex operator algebra. Then the first step is the usual step. We're restricting simply to the invariant subspace of the vertex operator algebra, which I'll call VG. So this is physically the untwisted sector. And then there's a statement, at least for G solvable, that if V is tame, then VG is again tame as well. But the point is, if V is holomorphic, then VG is no longer going to be holomorphic. In fact, for instance, it's going to have a lot of irreducible modules. For instance, if G happens to be the cyclic group Zn, and this is the case that we'll be interested in, cyclic orbifolds, then it turns out that this VG has n-square irreducible modules. So in order to turn VG into something which is holomorphic again, we need to add in back some of the modules, the so-called, well, physically this means we need to add back in twisted sectors. The question is, can we do that, or for what orbifolds can we do that in such a way that the resulting vertex operator algebra, this orbifold vertex operator algebra, is again holomorphic? And at least for cyclic orbifolds, there are conditions, but the conditions are essentially level matching. So fairly recently, the mathematical theory of this cyclic orbifolds has been worked out in complete rigor, and indeed what the Van Eekeren, Muller, and Schenkauer found is that effectively the only condition is level matching. So level matching simply means that the weight of the ground state in the twisted sector has to be compatible with the fractional moding of the modes of the Heisenberg algebra. So the point is, in particular, this moding, this fractional moding, is given by 1 over the order of the automorphism group. So what can happen is, and coming back to this point that one can try to find more complicated lifts of a lattice symmetry. If the most naive lift leads to violates level matching, what you can try to do is you can try to find a more complicated lift which has a higher order, which then potentially does not violate level matching. So in some cases, indeed, we find that sort of the most naive lift, the standard lift, would give an anomalous orbifold, but then if we use a non-standard lift, in some cases at least, we then find a non-anomalous orbifold. And basically, what I did together with my student Thomas Gemünden is we looked at cyclic orbifolds, and this is sort of the first step. The next step will actually be to look at more complicated orbifolds, non-abelian orbifolds, but this is technically somewhat more difficult. So let's give maybe the most famous example of this. The most famous example of a cyclic lattice orbifold is the Frenkel-Letowski-Merman construction of the monster vertex operator algebra. So this is, how do you do that? You start out with the Leech lattice, and then you orbifold by the lattice symmetry which sends x to minus x. This eliminates all 24 states of weight 1, because those 24 states are simply a single mode of the free boson which picks up the minus sign under the action of this symmetry here. And the resulting theory, the monster CFT, or monster VOA, has a lot of exciting properties. In particular, it has a monster symmetry, but actually we don't care too much about that aspect of the monster VOA. What you do care about more in the context of what we're doing here is that it's in fact an extremal conformal field theory as proposed by Höhn and Wittmann. So it's the extremal CFT for C equals 24, and extremal simply means that there are no spin 1 states. Now, if we're doing orbifolds of extremal lattices in D equals 48 and D equals 72, we actually need to do something more powerful than this simple Z2 orbifold, because the Z2 orbifold will eliminate all the spin 1 states, but now we actually also want to eliminate as many of, say, the spin 2 states, or maybe the spin 3 states as well. And the Z2 orbifold will, of course, not eliminate most of them. So what we're interested in is higher cyclic orbifolds. Again, eventually the goal will be to also consider non-cyclic, non-abelian orbifolds. But for a start, what we want to do is we want to systematically explore all cyclic orbifolds of these extremal lattice vertex operator algebras. So for D equals 48, I think I already mentioned there are 4 extremal lattices known. They have been constructed explicitly, and in particular also their automorphism groups are known, or at least in 3 of the 4 cases the complete automorphism group is known. In the 4th case, I believe, a relatively large subgroup, potentially a subgroup of the full automorphism group is also known. Now what we can do is we can systematically scan through all cyclic subgroups of these automorphism groups. And we can check for every such cyclic subgroup if you can lift it to a symmetry which allows a non-anomalous orbifold. And if there is a non-anomalous orbifold, we can compute what the partition function is like. So we did that, and we found around 100 new holomorphic CFTs with central charge C equals 48. And the original motivation was to find something which has as few light states as possible. So just to give you an idea of how well we're doing, let me show you the best result. That's down here. So what we managed to find is a conformal field theory, a VOA, which has one state of weight 0, the vacuum of course, no spin 1 states, and 48 spin 2 states. Now the question is a bit, should we be happy about that? Is that a good result or not? Well, it depends a bit on how optimistic or how pessimistic you are. If you're optimistic, then you can compare it to the unorbifolded lattice vertex operator algebra, in which case we have 48 states of weight 1, and we have 1224 states of weight 2. So these are simply the free boson descendants. And then you could say, these numbers here are much smaller than what we started out initially. So from that point of view, you could be very happy with our results. But then on the other hand, if you're a bit more pessimistic, you could say, well, ultimately there's a theoretical optimum that we could try to achieve, namely an extremal CFT. And an extremal CFT simply has no spin 1 state, and the only spin 2 state is the L-2 descendant of the vacuum that is the energy momentum tensor. And as you can see, we're still quite a bit away from having only a single spin 2 state. And then let's talk about D equals 72. In that case, there is a single extremal lattice is known, and again, at least a subgroup of the automorphism group of this lattice is also known. And again, what we did is we scanned over all cyclic subgroups of this lattice, and we constructed the non-anomalous orbifolds. And again, here you can see our best result. It has no spin 1 states, 36 spin 2 states, and 408 spin 3 states. The original unorbifolded CFT has 72, 2700, and about 70,000 spin 3 states. So we're doing much better than here, but now again, if we compare it with the theoretical optimum, the extremal spectrum, we would want to have 1, 0, 1, 1, so we're quite a bit away from that. As I already mentioned, sort of the next goal that we're working on now is to go beyond cyclic orbifolds, and then we can try to see if we can actually significantly, or maybe not so significantly, improve on this light spectrum. Maybe very briefly, let me also mention some sort of more mathematical motivation for what we're doing. The point is that holomorphic VOAs, at least for C equals 24, are essentially classified. So there was this original proposal by Schellekens that there are exactly 71 such holomorphic CFTs of C equals 24. And very recently, after a long decade-long work of a lot of people, mathematically, one is very, very close to a proof of that. But for C equals 48 and C equals 72, one is extremely far from any possibility of classifying all possible theories. So in particular, we know that there is an exponentially large number of holomorphic vertex operator algebra. Simply by using the Siegel mass formula, we know that there's an exponentially large number of even self-dual lattices, and each of those will, of course, lead to a holomorphic vertex operator algebra. But our constructions, at least, even though they will only, they only fill out the minute part of all possible holomorphic CFTs for C equals 48 and 72, they give us at least some idea of what they might be out there. The other interesting remark is also that a lot of our constructions have 0 spin 1 fields, which suggests that their automorphism groups could actually be finite. So potentially, just like in the monster case, so potentially it might be interesting to look at some moonshine phenomena of these constructions. Okay, then in the remaining time, let me talk about a small application of what we found. So as you may have noticed, our goal is to be able to construct all these series very explicitly so that we can actually construct the spectrum and potentially also explicitly construct and compute other things. So let's talk about partition functions, and in particular higher genus partition functions. So what we're interested in is we would like to write down partition functions of such theories. In particular, what we look at here is partition functions of symmetric orbifolds, but this computation that I'll show you could also generalize it to permutation orbifolds. And in particular, what we'll be able to do is genus 1, which will be very straightforward, but we're also able to compute genus 2. So partition functions per se can be interesting. If you want to have a slightly more specific motivation, you can think of our goal as to be able to compute Renyi entropies and maybe eventually by analytic continuation also compute entanglement entropies. So the idea is the configuration for the Renyi entropy that we're interested in is the sphere with two intervals, which we'll set at 0, 1, y, and infinity. So y is the cross ratio. And then we want to compute the corresponding nth Renyi entropy, where in practice n is going to be 2 or 3. And then by the usual trick, we can map it to a n-fold cover. So for n equals 2, we get a genus 1 torus, and for n equals 3, we get a genus 2. Riemann surface. Okay, so we can do that for genus 1, and there the answer is actually extremely straightforward, because we know, if we know the spectrum, then you know the partition function for genus 1 simply depends on the spectrum. And so what we're interested in is we're interested in the large n limit of this partition function. So for finite n, of course, this partition function, the free energy, is going to be well defined. So, you know, the radius of convergence is going to be, so it's for all positive temperature, this thing is going to converge. However, if we take the large n limit, that is no longer necessarily the case. So we may encounter something like a Hagedorn transition if we do that. One example, if we go back to the symmetric orbifold, where I told you that the growth of the light states, and after the n to infinity limit, all the states are light. So we can simply plug in this growth behavior for the number of states here, and then we see it grows exponentially, and the radius of convergence is e to the minus 2 pi. So after the large n limit, actually, this partition function shows a Hagedorn transition. It becomes infinite if the temperature is beyond 2 pi. And in fact, it turns out that this is essentially the Hawking-Page transition. So it's sort of the dual interpretation is that the contribution of the vacuum dominates for low temperatures, and then at beta equals 2 pi, there's a sharp phase transition where the contribution of some BTC black hole dominates. But let me point out that this is actually what we've done is, strictly speaking, a different computation, because this argument here about the Hawking-Page transition in the bulk is an argument essentially using pure gravity, just classical Einstein gravity or maybe semi-classical Einstein gravity. Whereas here, what we did here is we did a computation in the symmetric orbifold, and the symmetric orbifold point is very much in the stringy regime. So in that sense, it's not at all obvious that this nice and clean Hawking-Page transition should still happen at the symmetric orbifold point. So in that sense, it's not completely obvious. But it turns out that for symmetric orbifolds it works, and actually one can show that this Hawking-Page transition is quite universal. Basically, if you have a theory whose light states, roughly speaking, do not grow faster than e to the 2 pi h, so they do not grow faster than the symmetric orbifold, you do get, again, the standard Hawking-Page transition for genus 1. So for genus 1, this Hawking-Page transition, this phase transition that we encounter is very universal. And now the question is, if you go to genus 2, is it still as universal? And it turns out that things become much more interesting there. So let me write down very schematically what the genus 2 partition function looks like. And the important point here is that now it does not only just depend on the spectrum, but it also depends on the 3-point function, or precisely the square of the 3-point function. So the idea is this is the partition function on some genus 2 Riemann surface, and what we did is we did a pair of pans decomposition. This is where the square of the 3-point functions come from. And now the question is, what's the radius of convergence of this thing in the large n limit? And in order to compute that, we need to be able to compute 3-point functions. And in principle, one can compute 3-point functions of permutation orbifolds, even for finite n. So this has been worked out by series of paper by Louis Montour and Leonardo and friends, but in practice it's quite painful. And what we're actually going to do is we're going to go to the large n limit immediately, and it turns out in the large n limit things are much easier. Basically what happens is that the theory, the symmetric orbifold theory, and actually also certain classes of permutation orbifold theories become free. And free in that case means that the correlation functions are simply can be obtained by counting all possible Wick contractions between the fields. So basically everything reduces to simply count some combinatorial counting, and it turns out that if we pick some particular 3-point function of certain fields, these correlation functions. Think of them, so the computation that we're doing here is in the symmetric orbifold, but just think of them as a free theory where you have some field phi to the k1, phi to the k2, phi to the k3, and then you just take the, you just count all the big contractions. Then the statement is, even for the symmetric orbifold, you get the same result, at least to order 1. So there will be order 1 over square root and terms, but we will forget about them. And then the important and interesting thing is that actually this, if you specialize, for instance, to k1 equals k2 equals k3, you find that this 3-point function grows exponentially, which means that, potentially the genus 2 partition function has a more interesting radius of convergence because the coefficients grow exponentially. And so in particular, you can plug it in. So if you take, say, some seed field which has weight h1, you have, roughly speaking, this growth here, or at least the dominating contribution is this growth here. And then if you plug it into the expression of the genus 2 partition function that I wrote down, what you find is that the radius of convergence is smaller than y equals 1/2 if this seed field has a weight smaller than 0.17. So if there is a very light field, then the radius of convergence is smaller than y equals 1/2. Why is 1 equals 1/2 important? Because at y equals 1/2, we expect the phase transition anyway, simply coming sort of from the Ryu-Takanayagi analog of the Hawking page transition. But if there's if the radius of convergence is smaller, then y equals 1/2, that suggests that there is some new phase in the theory. So that adding these additional stringy states coming from the permutation orbifold or from the symmetric orbifold lead to a new phase in the genus 2 partition function. So this is work together with Alex Bella and Aida Sade, and indeed this suggests that for genus 2, the phase transitions are much less universal than in the genus 1 case, where basically you could take any symmetric orbifold and you still got the same phase diagram. Here, if you take a light enough field in the symmetric orbifold, you find that there is a new phase. Also, let me point out that even though the way I presented this computation was in the framework of symmetric orbifolds, again, this counting is the same for simply free theory. So for instance, if we just have a scalar with weight h1, we would get exactly the same growth and exactly the same behavior of the radius of convergence. And now in the remaining 2 minutes or so, let me advertise work by our friends Don Maguire, Maloney, and Maxfield. So what we did is we did a computation on the CFT side. And this made a prediction that there should be a new phase appearing if there's a light enough scalar, if there's a light enough field in the theory. Now, of course, what you would want to do is you would want to check if you can sort of confirm this prediction on the gravity side, on the bulk side. And this is exactly what these people did. Basically, what it boils down to is you're interested in an eigenvalue problem of the Laplacian on ADS3 with genus 2 boundary conditions. So the idea is you place some field of, say, mass squared mu, where this is the usual relation between h and mu coming from relating the mass of the field to the weight of the dual operator. And then what you want to do is you want to check whether the vacuum is still stable under perturbations. And this basically boils down to computing eigenvalues of this operator here. If you find negative eigenvalues, then this suggests that if you perturb a little bit the vacuum by turning on this new scalar field, this massive scalar field, then it will start rolling away to some other minimum, which indicates that there's a new phase. And very surprisingly, at least to us, they found that this exactly happens for exactly the same number that we found. So they also find that this happens, that you find negative eigenvalues if h1 is smaller than 0.17. So I should say I cheated a little bit here because there are certain approximations here. So we were confident that some effect like this would happen, but we were not very confident that this was the optimal bound. But very nicely, they find exactly the same answer here. So this is a very, very nice test in my view of the ADS-CFT correspondence. Let me just stress that this is actually, we're not using anything supersymmetric or anything. This is a very straightforward, in a sense, bosonic computation, and we do get the exact precise value. Okay, and with that, I'll finish. Thank you very much.